Estimate the radius of gyration and end-to-end distance of a polystyrene sample having molecular weight 1 times 10 to the power 5 grams per mole. Square root of Rg squared over m, where Rg is the radius of gyration and m is the molecular weight, is a constant for a given polymer and is independent of the molecular weight. So light scattering and small angle neutron scattering studies have shown that the values in theta solvent and in the bulk state are identical. It is found that the random coils also exist in the bulk amorphous state. For random coils, end-to-end distance is given by R is equal to square root of 6 Rg. From table 5.4, we have for polystyrene square root of Rg squared over m given as 0.275 Armstrong, square root of mole per gram. So Rg is equal to 0.275 times square root of 1 times 10 to the power 5. So that gives us 87 angstrom. Now for random coils, end-to-end distance R is given by root 6 times Rg. So that would be root 6 times 87, and that comes to 213 angstrom. In an actual kitchen experiment, 1 quart of cooked spaghetti was measured out level with cold water so that the spaghetti strands just break the water surface. 9 ounces of water were drained. Assuming the spaghetti strands were polymer chains, what is the ratio of the specific volumes of the perfectly packed state to the actual disordered state? Assume a hexagonal close-packed array. Hint: allow for water between perfectly aligned spaghetti strands. Calculate the average angle between strands, theta by 2, given by the ratio of the specific volumes. Specific volume is the reciprocal of the density. Interpret theta by 2 in terms of intermolecular orientation and the randomness of the amorphous state. For part A, assume that this is the container and this is the spaghetti strands. And then they're adding water such that it just covers up all the strands. So the water will occupy the spaces in between the strands, which means total volume is equal to volume of spaghetti, of the cooked spaghetti, plus volume of the water drained. So the total volume is 1 quart, and 1 quart is 32 ounces. So the total volume 32 equals volume of the cooked spaghetti plus the water drained, which is 9 ounces. So volume of spaghetti is 23 ounces. Packing fraction for this cooked spaghetti is volume of spaghetti, which is 23 ounces over 32 ounces, which is 0.72 or 72%. In a hexagonal closed packing, Atoms are arranged in the corners of a hexagon in a lattice structure, and there is one atom in the middle of the hexagon, and then in between these two layers of hexagon there are three atoms which fill in the void. These three atoms fill in the void that is created when we pack these atoms in an hexagon. So we have to assume that these are packed like this, touching each other. So if this distance is a, and if the radius of the atom is r, then a is equal to 2r. So the next layer will have atoms here in these voids, and then again the layer above will have atoms like this, which are right above the lower hexagonal layer, and so on and so forth. This layer is similar to the one here, and this is the middle one, and the one in green is the lower one. So, and so on and so forth. In 3 dimensions it extends, and that's the lattice structure. Now each atom in the corner of the hexagon is shared by 6 other unit cells. So the contribution of each atom to a unit cell is 1 by 6, and there are 6 of them in one hexagon, and there are 2 hexagons, so that times 2. Plus, if you look at the atoms in the center of the hexagon, they will be shared by 2 unit cells, right? One which is depicted here and the one that is above it. So, and there are 2 of them, so it's 2 times 1 times half plus the ones that are filling the void and that are in between the 2 hexagons. They are present only in this lattice cell. They are totally inside. So each atom is totally inside the lattice cell. So it's 3 times 1. So this gives us 2 plus 1 plus 3. So there are 6 atoms per unit cell. The volume occupied by these 6 atoms would be 6 times 4 by 3 pi r cube, assuming they are spheres and r is the radius. Volume of this hexagonal unit cell would be (6√3 by 4) times 4r squared times c, where c is this distance. It can be shown that c equals 2√2 times 2r over root 3. So if we divide the volume occupied by the atoms over the volume of the unit cell, we get a ratio of 0.74. So the ratio of specific volumes of the perfectly packed state to the actual disordered state is 0.74 is to 0.72, which is 1.03. So substituting Vc over Va, the ratio of the specific volumes in this equation, plugging in theta equals 180, then theta by 2 is 90 degrees, and plugging in various values of theta, like theta is equal to 90, then theta by 2 is equal to 45. Theta is equal to 0 is not possible because sine theta by 2 in the denominator cannot be 0. Trying various values, the closest value is when theta is equal to 180 degrees, making theta by 2 is equal to 90 degrees, which gives the closest value to 1.03. So the average angle between the strands is 90 degrees, which means that there are strands equally distributed between 0 degrees and 180 degrees. So it is completely random. So it's totally amorphous. With the advent of small angle neutron scattering, molecular dimensions can now be determined in the bulk state. A polymer scientist determined the following data on a new deuterated polymer dissolved in a sample of protonated polymer. The values of d sigma by d omega to the negative 1 are given, and k squared times 10 to the power 4 Armstrong to the negative 2 are given. The constant Cn for this system was determined to be 10.0 times 10 to the negative 5 moles per gram centimeter. What is the radius of gyration of the deuterated polymer? What third quantity is implicit in this experiment, and what is its probable numerical value? We can start off with the equation used in small angle neutron scattering experiments. D sigma by d omega to the negative 1 equals 1 over Cn times the molecular weight mw times 1 plus k squared, where k is the wave vector, times rg squared, where rg is the radius of gyration, over 3. So this is of the form y equals mx plus b, equation of straight line. So if we have a plot of d sigma by d omega to the negative 1 versus k squared, then 1 over Cn mw rg squared over 3 would be the slope, and 1 over Cn mw would be the y-intercept. Let's plot the graph. So the k squared times 10 to the power 4 Armstrong to -2 goes from 1.00 to 10.1 in values. So I'm going to start from 0. d sigma by d omega to the -1 has values from 0.5 to 1.20. So the first point is 1.00 and 0.5. The second coordinate is 3.70 and 0.72. The third coordinate is 10.1 and 1.20. So this is the straight line. So we get the y-intercept as 0.4 centimeter, but our y-intercept is 1 over Cn mw, and Cn is 10.0 times 10 to the -5 moles per gram centimeter. So mw is 25,000 grams per mole. Now for the slope, one over Cn mw rg squared over 3. Let's select 2 points from the graph. 1.2 times 10 to the -4 and 0.5. 1.2 times 10 to the -4, because the x-axis is k squared times 10 to the 4, so we want to write 1.2 times 10 to the -4, and the y-coordinate is 0.5. The other point, 5.2 times 10 to the -4 and 0.8. So the slope is which is equal to 750 centimeter Armstrong squared. So that's a slope. 750 times 10 to the -16 centimeter cube. So Rg equals slope times 3 times Cn, which is 10.0 times 10 to the -5 mole per gram centimeter, times the molecular weight, which is 25,000 grams per mole, and the square root of that. Which is 75 times 10 to the -8 centimeters, or 75 angstrom. We can compute Rg squared over mw, the square root of that, which is a constant for a given polymer and which is usually expressed in angstrom mole per gram to the power half. So that would be square root of 75 squared over 25,000, 0.474. For a polymer in the bulk state, it is present as random coils. The end-to-end distance R is given by square root of 6 times Rg. So R, the end-to-end distance R would be 1.16 angstrom. For this equation, A2, the second virial coefficient, is taken as 0. This is because A2 denotes polymer-solvent interactions, and in this case, the polymer is dissolved in the deutero form of the polymer, or the deutero-substituted polymer. So it's essentially the polymer is dissolved in itself. What is the activation energy for a three-armed star diffusion coefficient in table 5.9? Assuming an Arrhenius relationship, how do you interpret this result? Assuming Arrhenius relationship, the equation relating the diffusion coefficients d1 and d2 at two different temperatures T1 and T2 would be ln d1 over d2 equals negative EA over R times 1 over T1 minus 1 over T2, where EA is the activation energy and D1 and D2 are the diffusion coefficients at temperatures T1 and T2. So R is the gas constant and T1 and T2 are expressed in Kelvin. So this would be the relation between D1 and D2 at two different temperatures T1 and T2 if they followed an Arrhenius relationship. Plugging in the values from table 5.9, D1 is 2.4 times 10 to the negative 14 centimeters squared per second, and D2 is 1.4 times 10 to the negative 13 10 centimeters squared per second. (8.314 joules per mole Kelvin), and the temperatures are 1 over 125 centigrade, which is 398 Kelvin, 165 centigrade, which is 438 Kelvin. So this gives us an EA value of 73.163 kilojoules per mole. So to get some perspective, room temperature is 25 centigrade, which is 298 Kelvin, and RT at room temperature would be 8.314 times 298, which is 2.4 kilojoules, which means about 25 times of energy is needed for diffusion to happen. Let us find out what the diffusion coefficient would be at room temperature using Arrhenius. 2.4 times 10 to the negative 14 centimeters squared per second over d1 at room temperature, which is unknown, equals negative 73.163 kilojoules per mole times 8.314 joules per mole Kelvin times 1 over 398 minus 1 over 298, which is the room temperature. So D1 is 8.73 times 10 to the negative 18 centimeters squared per second. So the diffusion coefficient at room temperature is much more less. If we look at the table 5.9, we can see that the linear polymer, the linear polybutadiene, has a diffusion coefficient of 4.8 times 10 to the negative 11. Centimeters cubed squared per second. Since the molecular weight of the linear polymer is almost the same, it's 7.3 times 10 to the power 4 grams per mole, which is almost the same as the three-armed polybutadiene, which is 7.5 times 10 to the power 4 grams per mole. And both are at the same temperature, which is 125 degrees centigrade. Let us find out what would be the activation energy for the linear polymer, assuming that the Arrhenius constant would be the same. EA for the linear polymer would be the activation energy for the star polymer plus ln of the diffusion coefficient of the star polymer over the diffusion coefficient of the linear polymer. And we get the activation energy for the linear polymer as 48 kilojoules per mole. So we can see that the activation energy for the linear polymer is much less than the activation energy for the star polymer. That is because the star polymer has to align the three arms in the direction of diffusion, whereas the linear polymer does not have to do that. So the star polymer experiences a decrease in configurational entropy for diffusion, and so its activation energy is much higher than that of the linear polymer.